In the previous video, we had done the in-text questions. In this video, we are going to be talking about the textbook questions. First of all, to recap the periodic table, we had started from the history or the genesis of the periodic table. We had learned about different types of the periodic table. That is, as in, not types, as in the various systems of classification that were used before the modern periodic table came around. We had then learned about the modern periodic law and the present form of the periodic table, the IUPAC nomenclature, the electronic configuration of elements. That is why so many elements in each period of the periodic table. That is, of course, to do with the principal quantum number in each case. And then we also learned about the various trends of the periodic table. That is, we learned about atomic radius, ionization enthalpy, electron gain enthalpy, and about the chemical properties and also the electronegativity. So let's start. First question. What is the basic theme of organization in the periodic table? So the reason, first of all, we have periodic table is for us to easily understand and differentiate between various elements. So the basic theme is for us to study, systemize the study of various properties. And this is done to ensure that the similar elements are kept together and the dissimilar ones are kept apart. So it has actually made it quite easy to remember the properties of elements. I mean, if you look at all the elements and if they're arranged in a haphazard manner, obviously it'll be quite difficult for us to comprehend the atomic, for example, the atomic radius. How can we just say that, let's say sodium has a bigger atomic radius than chlorine? So it's quite difficult to comprehend if it was all random, but because it's arranged in a particular order, it's made it easy for us to understand various properties. Next one, second one. Which important property did Mendeleev use to classify the elements in his periodic table, and did he stick to that? So Mendeleev actually, when Mendeleev was working on his periodic table, the concept of atomic number hadn't even come up. So the discovery of electron, proton, and neutron were actually after, right? It was in the end of the 19th century and the beginning of the 20th century. So the concept of atomic number didn't exist then. So all they knew was atomic weight. So what he did was he arranged these elements with respect to the atomic weight, and he ignored the values of atomic weights in some cases because he had assumed that the calculations were wrong, and he was right with respect to that. For example, uranium was considered to be just 120 as its atomic weight, but later it was found to be almost double the amount. So iodine, for example, was placed after tellurium. There was a 0.7 or 0.8 difference between the two masses, where iodine was lesser than tellurium. But because he wanted bromine and fluorine to be along with iodine, so he placed iodine after tellurium. So he himself didn't follow, he didn't stick to his law because the properties didn't match up. So he changed it accordingly. So he placed iodine so that it was in the same group as chlorine and bromine. So he did not, the property he used was atomic weight, but he ignored that particular thing in some cases. What is the basic difference in approach between Mendeleev's periodic law and modern periodic law? I mean, the basic difference between the two, as I just said, is the fact that Mendeleev used atomic weights, whereas the modern periodic law is to do with the atomic numbers. So because the atomic weights posed a lot of issues, and there was questions about, if you remember, he had discussed about the disadvantages of Mendeleev's periodic table. So it's to do with respect to that particular reason as to why, we shifted to atomic numbers. So they're both properties. So the properties of elements are the periodic function of their atomic weights. Physical and chemical properties of the elements are the periodic function of their atomic numbers. Fourth question, on the basis of quantum numbers, justify that the sixth period on the periodic table should have 32 elements. Now over here, since it's the sixth period, n equals to 6, and the available orbitals are 6s, 4f, 5b, and 6p. This is to do with their energies. So if you haven't learned about the various orbitals and their energy levels, you have to learn about them in atomic structure. So the total number of orbitals which are available is 16. The reason this is the case is because S you have 1, F you have 14, sorry, F you have 7, D you have 5, P you have 3. So 3 plus 1 plus 7 plus 5 equals 16. So the number of orbitals available are 16, and the number of electrons that can be filled are 32. So there'll be 32 elements in the sixth period. In one of the in-text questions, I believe it was the fifth period, why does it have 18 elements? But here we're talking about the sixth period, and so you, based on the number of available orbitals, we are figuring out the number of electrons. So in terms of period and group, where would you locate the element with Z equals to 114? So the atomic number of radon is 86. So 114 minus 86 equals to 28. So number of electrons that have to be filled are 28. And since we know that this element radon is in the sixth period of the periodic table, we know that this particular element will be in its seventh period. I would suggest for you to remember, the atomic numbers, at least of the elements of the inert gas group. It's advisable that you remember that. So it's easier for you to understand that which shell should be filled up, and like you don't have to start from 1s2, right? So you need not fill 86 electrons. I mean, that's pretty taxing. So instead, you can just start from radon, whose 86 electrons are already filled, right? You have 28 electrons left. And since this element is in its seventh period, you have 7s2. Then, of course, you'll be filling up the 5f14, 60, 10, and 7p. This is with respect to their order, their order in terms of increasing principal quantum numbers, but you can just write it as 7s2, 5, 14, 60, 10, and 7p, 2. So n equals to 7, so the element will be in the seventh period. And since there are 2 electrons in the p orbital, the element will be in group 14. Next. That's because this you can easily figure out with respect to the noble gas configuration. Noble gas will have 6 electrons in the p shell. 6, this only has 2, so it's so many blocks. Okay. 4 blocks before the 18, that's 14. Next one, write the atomic number of the element present in the third period and the 17th group of the periodic table. Since it's in the 17th group, its electronic configuration is Ns2, Np5, that's halogens. And since it's in the third period of the periodic table, N will be equal to 3. So 3s2 and 3p5. Which element do you think would have been named by Lawrence Berkeley Laboratory and Seaborg's group? So lawrencium, whose atomic number 1 is 103, was named by Lawrence Berkeley Laboratory, and seaborgium, whose atomic number is 106, has been named by Seaborg's group. Next one. Why do elements in the same group have similar physical and chemical properties? So every single property in the periodic table that we had learned about is directly dependent on the electronic configuration. And since all the elements of a group will have the same electronic configuration, they will have similar physical and chemical properties. Think about it. Why do you think that the word similar is used, and instead of similar, it could have just been same, or same chemical and physical properties? The reason is the fact that if you think about halogens, you have bromine is a liquid, iodine is a solid, fluorine is a gas. So the physical properties are quite different from each other. So we do not say that they all have same physical properties and chemical properties, because in each case, you will have an exception. The next question. What does atomic radius and ionic radius really mean to you? So the word atomic radius is actually a combination, is to denote both the metallic radius as well as the covalent radius. Now, the covalent radius is used for nonmetals, and it is 1/2 of the distance between two nuclei of covalently bonded atoms of the same element. So if you have hydrogen and hydrogen, H, one bond, and half the distance is the covalent radius. Metallic radius is half the internuclear distance separating the metallic or metal cores. We'd learned in detail about the covalent and metallic radius when we had discussed about the atomic radius and their variation across the period and down the group. So if you haven't, you have to check it out. Um, Ionic radius. So what does it mean? The effective distance from the nucleus of the ion up to which it has an influence on the ionic bond. So the ionic radius is actually quite difficult to predict because the ionic bond is formed between two different elements. And unlike in covalent metallic, we had it as the same element, but in case of ionic, there are two different elements. So we can only predict it, and the radius is the effective distance from the nucleus of the ion up to which it has the influence on the ionic bond. How do you explain, how do atomic radii vary in a period and down the group? How do you explain the variation? So across the period, the atomic radius decreases, and down the group, atomic radius increases. Across the period, there is a decrease, and this is because despite the number of electrons increasing, the the effective nuclear charge is also going to increase. So it is able to pull the electrons towards itself. Down the group, despite all of them having the same outermost electronic configuration, the electron is not getting added to the same shell, it's getting added to the next shell, which means the electrons getting added, and that particular force is, and the nuclear charge is not increasing as much as the distance. So because there is an increase in the number of shells, the atomic radius is increasing down the group. To understand this in detail and very well, do check out the video where we discussed about the atomic and ionic, rather the atomic radius. There was another one about ionic. Okay, so with that, we finish the first 10 questions. To check out the next 10 questions, go to the next, check out the next video.